Alright, and welcome back, and we'll finish up this example. I had to reshoot this video, so if it seems like there's a little bit of a jump or disconnect, not exactly matching up, that's the reason why. So, starting back into this, we broke down, or we figured out the forces that are being applied, and we came up with our unbalanced equation here. So now we need to go through and plug in our calculations. So FGXB, we know that that's going to be the driving force. We decided it's a clockwise motion, so we're going to end up with mass 30 times our gravity, and it's on an angle, so we have sine 60 minus our force due to friction on that block B. So that's going to be our mu value, so 0.3, and we're going to multiply that by normal force, which would be 30 times 10 times cos 60. I'll carry down on the next line, minus, still those first two are taken care of. On to the third one, the friction from block A. So that's your mu, 0.2, multiplied by the normal force, so 20 times 10 times cos 40. And then we got to take into account the gravitational force of A, which is opposing motion, so minus your mass, 20 times gravity, multiplied by sine 40. And that all adds up to our mass times acceleration. So it's our total mass of the system, because we're analyzing the entire system, and accelerations are unknown. So that will reduce down, or simplify down to, so the first one we'll have is 259.8 minus 45 minus 30.6. So if you just check in your calculator, make sure you can get the same values. That's what it simplifies to, 50A. So once we go through and solve for A, we get an acceleration of 1.1 meters per second squared clockwise. So that's good. That means that we predicted properly. We predicted the right direction for motion. So that calculates the acceleration of the system. Now, we want to go back and we want to find the tension force. So our free body diagram that we did create here for block B is what we're going to use. So that means that we are using the x component here. So these three vectors here. So in that direction, so right down here, we're going to find tension. So according to this, tension and friction are in the same direction. So this is where it's up to you as to which you want to do in terms of sign direction. I'm going to say negative tension because I'm going to say the motion is the positive direction. So as long as you're consistent, it doesn't really matter which way you have your signs. So because tension and friction are heading in the opposite direction, they will be a negative, plus your FGX. It's the driving force pushing it down the slope, and it's equal to mass times acceleration. So from that, we can plug in our values. We're looking for tension, so that's the unknown, minus your force of friction. I guess this is for block B. All right, so block B, it'll be, again, doing our calculations from up here, 0.330 times sine 60. I always make sure I do this in the right direction. Sorry, cos 60. Cos 60 plus FGX. So that is your mass times gravity. Oops, and I forgot gravity on the friction. 30 times 10 sine 60 equals mass. So now we're just analyzing that particular block, block B, so it's 30. And we know our acceleration, we just calculated it as 1.1. So now we go ahead and we can clean this up a little bit. So we calculate that through again. So your force of friction for object B, if we had 45 newtons from above, plus your FGX, also calculated from above, 259.8 equals your 30 times 1.1, you get 33. The only thing you gotta be careful with, I have tension as negative, so I'm going to move it to the other side. So for argument's sake, I'll write it out one more time. Now the 33 is going to come across and be negative, and now I have tension as a positive. So I go ahead and do that calculation. Minus 33, and we get 181. So that is the tension in the string. All right. So basically what you do, again, one last time just to summarize the process here, you draw your free body diagrams. That way you know all the forces that are acting along the incline. You find system acceleration. All right. And once you have your system acceleration, like we did the 1.1, you then return back and you look at the individual components. So you analyze the driving component. And it really wouldn't matter. You could look at block A as well. The free body diagram will come out the exact same, but for argument's sake, you can, I just picked the driving block anyway. And you reanalyze your free body diagram. So the tension or the calculation then for that comes straight from that free body diagram. And that's why those free body diagrams are so important, because that's where we build our equations from. If you have any questions, let me know, and good luck on the homework in this section.